Okay, so today we're going to be solving this related rates problem. A man standing 12 feet from the base of a lamppost casts a shadow 4 feet long. If the man is 6 feet tall and walks away from the lamppost at a speed of 100 feet per minute, at what rate in feet per minute will the length of his shadow be changing? So I would first recommend drawing a picture of this scenario. Okay, so here we have a man and he is 6 feet tall. His shadow will represent with S is going to be 4 feet. The distance he is from the pole will go right here, that's X, and he is 12 feet. And then we're not sure of how tall the lamp is, but we can solve for that height using similar triangles. So if you are unsure about similar triangles, I'd recommend watching my video on that. But basically, because these two triangles, this little triangle right here, and then obviously the larger triangle right here, because these two triangles share an angle right here, and then they both have a right angle, that means that this last angle in each of their corners must be congruent because all of the angles need to add up to 180 degrees. So these are definitely similar triangles, and I can create a ratio of their side lengths that is true because they are similar. So we can say that on the little triangle, this 4 and this 6, those have a ratio, 4 to 6, that has to be congruent or equal to the ratio of the bottom of the big triangle and the side of the big triangle. And we'll call this H over here. So the bottom can be represented by 12 plus 4 because of this X plus this 4. And then the side is obviously going to be H. Now I can solve for H. If I simplify this down, I'll get 16 over H equals 2 over 3. And now if I cross multiply, I'm going to get 48 over H. 48 equals 2H, and so H equals 24. So using similar triangles, we figured out that the height right here is going to be 24 feet. Okay, now I want to figure out the rate at which the length of the shadow is changing. So that's going to be the shadow, but the rate at which it's changing is going to be ds over dt. So if you ever see rate, you need to think derivative with respect to something else. And along those lines, I see that he's walking away at a speed of 100 feet per minute. So a rate can also be written as something per something else. So in this case, it's going to be feet per time. And he's walking away. That would be that our x value is changing. So we'll call that dx over dt. And that's going to equal 100. And so now I need an equation that relates x's and s's because I just want to get the rate of dx to be similar or in an equation with ds. And so in order to do that, we're going to come back to this ratio of similar sides, but instead of plugging in s and x, I'm going to keep s and x. So the bottom of this triangle we can represent as x plus s, and then that has to be similar to the bottom of the smaller triangle, which is just s. And now the ratio, well, I know the side of this is going to be, I don't have a variable for it, but I'm going to plug in a number because I already have my equation with x's and s's. And then on the bottom of this fraction over here, I need to have our height, which we solved for, was 24. So now I can cross multiply again. I'm going to get 6x plus s equals 24s. Now I'm going to divide by 6. I'll get s plus s divided by 6 equals 4s. And now I'll subtract s over, subtract s, x equals 3s. So now I have related s and x, so I just need to take the derivative of both sides. So I'm going to get dx over dt on the left side equals 3 ds over dt on the right side. And if I solve for ds over dt, I'll get 1/3 dx over dt equals ds over dt. And from the beginning, we figured out that dx over dt equals 100, so I can plug that in now and get 100 over 3 equals ds over dt. And the units on that is going to be feet per minute, just like dx over dt. All right, thank you.